Okay, we're continuing on here. 14. We got into buffers last time. And remember that buffers are solutions that can resist change in the pH when acid or base is added to it. So as we talked about last time, remember a buffer is not necessarily always a neutral solution. As we played with today, again, there's buffers of 4, 7, 10. You can make a buffer at any pH you want. The deal is it basically will be able to maintain the pH of where it's at when you do add acid or base to it. The reason it's able to do that is it's able to have two things in there, either a weak acid and the salt of its conjugate base, or a buffer could be made up of a weak base and the salt of its conjugate acid. And they both are basically in the solution at the same time. So there's an acid part and there's really a base part to a buffer that is floating around in the solution to begin with. That means when you add more acid or you add more base to a buffer solution, ultimately it's able to maintain the pH by preventing the formation of free H plus when you add acid, or free OH minus when you add base. So by really preventing the concentrations of either the H plus or OH minus from going up when you add acid or base, it is basically able to keep the H plus concentration relatively constant, and it will be able to maintain the pH as to where it's at. As we talked about, though, if you were monitoring it with a pH meter, which we'll do, you would see the pH change a little bit, but we won't see a big jump in pH like we would see, for example, in water, which is not a buffer. In water, when you add acid, you pretty much generate a lot of H plus in that solution super quick. And because the concentration of H plus goes up really, really quick in water, when you add acid, we see a very big jump in the pH. And the same thing would happen if you add some base to water. You would generate a lot of free OH minus really, really quickly. And remember, OH minus and H plus are tied together. So as one goes up, the other goes down. So as the OH minus concentration would go up, the H plus concentration would go down, and you would see a big jump in the pH going upwards and more basic in that case. So by able to preventing that formation of either of those things, it's able to keep the pH relatively constant. We cannot have a buffer that is made up of a strong acid or strong base, because the strong acid or strong base will 100% ionize or dissociate, which means it cannot keep both of those things in the solution at the same time. It cannot keep the acid and the base part floating around, which is what you need. You would only have one or the other. You'd have either the acid part or the base part, but you wouldn't have both. And that is essential to the function of a buffer, is basically having both of those parts available. And as we talked about, one of the other things that we do see when we add acid or base to the buffer is, for example, when we do add acid, we will use up some of the base, but we will make the other part of the buffer. So, we'll use up a little bit of the base part, but we will make more of the acid part of the buffer. And same thing here, if we add some base, we will use up some of the acid part and make some of the base part of the buffer. So one of the sort of benefits and why a buffer can kind of work over a good period of time is, even though you may be using a part of the buffer, you also are regenerating sort of the other part of the buffer, and that allows it to basically maintain. As we also talked about, there is what's referred to as buffer capacity. There's a limit to how good or effective a buffer could be. If you grab something that is way too concentrated for your buffer, Or if you just keep adding, for example, acid and acid, keep adding and adding and adding it, eventually you'll eat up all the base part of the buffer and it will not be able to maintain its pH. A buffer really is a common ion effect type situation that's occurring because you have basically the weak acid conjugate base or the weak base and conjugate acid in solution. And that really means for most cases, we do want to use the Henderson-Hasselbalch equation. The pH is equal to the pKa plus the log of the base over the acid. Once again here, the pKa value is minus the log of the Ka value. A similar equation that does POH that you will sometimes see, but again, as we talked about, I don't really see the benefit of using this, but is the POH is equal to pKb than the pH one. And obviously you're using a pKa versus pKb. pKb minus the log of the Kb, and again, the relationship between these two, pKa plus the pKb gives you 14. You also, if you have the pKa, you can get the Ka value by taking the inverse log of the minus pKa, just like we do kind of with pH and all that. And if you have the pKb, you could also get the Kb value from that by taking the inverse log of the minus pKb value, which once again is like a 10 and a caret pKb. We also saw that you could use the Henderson-Hasselbalch equation, which again is this equation here. For any type of buffer, it can be acidic, basic, or neutral. So that's really kind of the benefit of using it, because in most cases, as I mentioned, you're going to be asked to calculate the pH. So you might as well just kind of go into there. If you don't want to use the Henderson-Hasselbalch equation, you could still do an ice table. And remember that when you do the ice table, it is important that, for example, when you do the initial, you should have a number here. This should be 0. And once again, you should have a number on the other side, which is your conjugate acid or conjugate base. So again, if you zero out this side, you're not doing a buffered problem. If you choose to do a nice table, you're basically doing either a weak acid or weak base problem. So you got to make sure you do have that number. Any questions on any of that stuff we talked about, I think, the last time? Hope we talked about that last time. I think it sounded familiar. All right. So did we end up doing the first part of this last time or no? We just were talking. Okay, then let's start with part A first. So calculate part A. What is the pH of a buffer that contains 1 molar acetic acid and 1 molar sodium acetate? Ka value there for acetic acids on the bottom. Okay, let's take a look at part A here. So it does tell us it's a buffer, which means we can't go into the Henderson-Hasselbalch equation, or we can use an ice table, and it really is sort of your choice which way you want to go. If they didn't tell us it was a buffer system, we need to be able to recognize that it is a buffer system by just looking at these two things here, and they are related to each other. That's acetic acid and that's sodium acetate. If you get rid of the sodium, that is acetate, which means it's a weak acid and its conjugate base. I know, by the way, this is a weak acid because I see the Ka value down here, which tells me it is a weak acid. And again, this would be its conjugate base. So again, they will not always, in nice letters, write this is a buffer. You do need to be able to kind of look at it and recognize that it is a buffer situation that's occurring here. So since it is a buffer, I'm going to go into the Henderson-Hasselbalch equation here, and we're going to solve it. So the Ka value was 1.8, right, times 10 to the minus 5. We have a concentration of acetic acid, which is 1 molar. We have a concentration of sodium acetate, which is also 1 molar. So getting our pKa value, which would be minus the log of the Ka, minus the log of 1.8 times 10 to the minus 5 should be 4.74 when you calculate it. So now that I have my pKa value, I can calculate my pH by going into here. pH would be 4.74 plus the log. Obviously, this is the acid, which means this is our base. In this case, they are the same number, so you really can't screw that up, I think. So that is a log of 1, which equals 0, which means in this case, the opening pH here would be 4.74. Any questions on that part there? Now, if you did choose to do, say, the ice table instead, it would look again. You would take your weak acid and you would dissociate it apart. And initially you would have 1 here, you would have 0 here, and most important, you would have 1 there. So you got to make sure you have that guy. Change would be minus x plus x plus x, 1 minus x, x, 1 plus x. This obviously goes into your Ka. You solve for x. X equals the H plus concentration, and then you get to your pH again, which would get you basically the same answer, hopefully. So again, there's 2 ways you can do it. As we talked about last time, the Henderson Haas block might be a little less place or room for error, but you can definitely still do an ice table. Any questions on that there? All right, so let's talk about sort of what's going on here in part B of this. In part B, we want to know what is the pH of the buffer system after we add 0.1 molar HCl to it. In this particular example here, we're going to assume that basically everything has 1 liter for the volume. That's not always the case, but just to keep the numbers for this example, not too bad. We're just going to assume everybody just has a volume of 1 liter. So the earlier question was, do you need to do it in moles? And the answer for part B is you do need to do it for moles in part B. And I think we were touching upon this at the very end last time. Whenever you add volume from one sort of liquid to the next, or volume into things, the molarity will change. And again, the molarity changes because it technically is moles of solute per liter of solution. And obviously, as you keep adding more volume to each other, that bottom number starts to change. The part that really doesn't change is the moles. And the moles of solute is really, in any reaction, pretty much what's in there to react. So it's the moles of those guys that are floating around that's really doing all the reacting. So when we do any situation, like we are here in part B, where we have a buffer and we're going to add some acid to it or base to it, we want to do the ice table in moles. After you do the ice table in moles, you then want to convert back to molarity by dividing by the total volume. So whatever you added together, the total volume would be what you would want to use to convert it back. So that's really good practice. Moles on the first table, convert back to molarity after the second table. So if we look at this here in the second one, we're basically taking the same buffer, but we're adding 0.1 molar of HCl. So we're going to add 0.1 molar HCl to our 1 molar acetic acid, 1 molar sodium acetate buffer. And again, the same Ka applies here, 1.8 times 10 to the minus 5, which means the same pKa value also applies, 4.74. All right, so the first thing that's going to happen here is we're going to get a reaction. And when I add the HCl to my buffer, it is going to react with what thing? The acetic acid or sodium acetate? It is going to react with sodium acetate. That is an acid, and your buffer basically has an acid part and a base part, right? So the acid will react with the base part. And the reaction that we will get will be HCl will react with a little sodium acetate. And we're going to get basically a double displacement reaction where these two guys basically switch places. That's going to get you acetic acid and a little sodium chloride action happening here. So once again, we see kind of like what we talked about previously, that when we do this reaction, we will create basically part of the buffer as we create some acetic acid that is there. So that is the reaction, and we're going to do our ice table here. So initially here, we are going to do this guy in moles because we're adding the acid to our buffer. So we have a beaker of buffer sitting there, and we are adding it in. So because everybody is 1 liter, that means the HCl would be 0.1 moles. The sodium acetate would be 1 liter times 1 molar is 1 mole. And most importantly, here again, it is not a buffer unless you put the number on this side as well, which we have 1 mole. Otherwise, it is no longer a buffer what you're doing, and that will be it, really. Now, if this is a buffer, something slightly different as well, since we're doing this table of moles, when we add the acid to the buffer, we should expect what to happen to the acid we added. Should it still be there? Should it get used up? What should happen? This is a nice functioning buffer. The buffer should take care of the acid, right? So it should use up the acid. So unlike using X's, we actually know what the change is going to be here. The change should be really the HCl. It is like the limiting reagent. Yes, there's less of it, right? So the change here is actually going to be a number here, and it's going to be the moles of the acid. So that would be minus 0.1, minus 0.1, and plus 0.1 here. That means when we reach equilibrium, we will have 0 here. We will have 0.9 moles here, and we will have 1.1 moles here. Any question on the ice table here? At this point, it is really good practice to convert back to molarity. So in this case, since everything is 1 liter, will always be the case, you would have to add the volumes. But in this case, we're going to divide everybody by 1 liter, and that would be 9 molar, 1 liter, which would be 1.1 molar. You should always just sort of automatically convert it back to molarity, because in certain cases, we will continue on with the calculation and you will need molarity. So just to make sure you put it in molarity. I'll be honest with you, in this case, you won't make a difference if you use the Henderson-Hasselbalch equation, but you should definitely turn back to molarity. Why did I not do anything over here with this guy? What is that? Sodium chloride is a neutral salt, which means it's not going to mess up the pH. So might as well not throw numbers down where are going to want to use it wrong. Now, if you get to this point in the problem and, you know, you maybe are still frankly lost as to what's going on, which could happen, you do want to kind of use your ice table to help you. If we look at the ice table, frankly, we have this guy left over and we have this guy left over. And once again, we know that those two things are definitely related to each other. What we are left over with at this point is still a buffer. We have a weak acid and conjugate base basically left over. So don't overlook your ice table. It can kind of help you decide what you got left over. And because I know it is a buffer, that means that I could use the Henderson-Hasselbalch equation at this point and get the pH. Or if you're a fan of the ice tables, you could ice table it up one more time afterwards and not use the Henderson-Hasselbalch equation. So I'm going to go with the Henderson-Hasselbalch equation here. My pH will equal the pKa plus the log of the base over the acid. In this case, the pKa value will still be the same because it's based off the Ka value that we used previously, plus the log. Once again, we do want to get our base. And once again, this is our base, this guy. And that guy will go up on top. And our acid there will go on the bottom, which is this over here. Remember that the base will most likely, if it's a conjugate base, will have some type of spectator ion in it, like a sodium, a potassium, a lithium, something like that. And obviously this is the acetic acid, so that should be the acid. That means we take 0.9 divided by 1.1. We take a little log action of it. We add a little force 0.74 to it. We end up with a pH of 4.65. So we see a couple of things with our pH value here. First off, it did not too bad of a job, right? It maintained, right? It maintained the pH at 4.65. It started at 4.74, right? Did it move in the correct direction at least? It did. We added acid, which means the pH should go down. So again, if you did this calculation, you ended up with like 4.85. Although it did not change much, it changed in the wrong direction. So these are things you want to think about when you're doing your calculations, in case you invert a number or something like that. Any questions on that there? So earlier we were talking about the idea of, there is a limit to sort of buffer capacity. So let's just say we took this same buffer system and we made a mistake when we were doing the experiment. I'm sure that would never happen, but let's just say that happened. So let's just say we had our same buffer. So we had our 1 molar acetic acid and our 1 molar sodium acetate. And, maybe instead of, the 0.1 molar HCl, you grabbed out like the 18 molar HCl instead. It happens. It kind of looks similar, right? And we'll still keep everybody at 1 liter just to keep the numbers nice and simple. So once again, the HCl here is going to react with our sodium acetate. Giving us, once again, our acetic acid and our sodium chloride. So initially here, if we kept everybody at 1 liter and we're now going to convert it into moles, I now have 18 moles of this guy. I got still my 1 mole of this guy and my 1 mole of this guy. So what happens now when we get to the change part? What's going to happen? Will this buffer be able to handle that 18 molar that I just put in there? Between this guy here, the HCl, and the sodium acetate, which one is actually now the limiting reagent? This is sodium acetate, right? You only got like 1 mole of base there in your buffer to handle that. So what's going to happen in this particular case is the change is actually going to be this guy. You're pretty much going to blow right through it. And you would have a change in this case of 1 mole, minus 1 mole, and plus 1 mole. Which means when you do reach equilibrium in this accidental mistake, you'll have 17 moles of that, 0 of that. You'll still have 1.1 moles of this guy, which again, we could convert back into molarity, which would be 1.1 in this case. This is 1 liter. But when we look at what is left over at this point in terms of our ice table, we are left over with HCl, right? And we are left over with acetic acid, and we do have some sodium chloride there. Obviously, the sodium chloride is still neutral, right? Do we still have a buffer at this point? These two guys are not related to each other, right? This is no longer a buffer. What we have here is a strong acid, right? Which will pretty much generate a ton of H+, right? And we have a weak acid as well. We actually are left at this point with 2 acids, a weak acid and a strong acid, which will also have some H+ generated, which means we have just made our H+ concentration go way up. And we would definitely expect the pH to go way down. And we would see a really big jump in pH at this point because we are generating a lot of H+. Yes, sir. It would be in this case, it would be 2, some bad math, All right. So even worse, you'll have a couple more H+ there, so just 2 more. But it would be 2 more, thank you. But the take-home message here is obviously we blew through our buffer and we would have just really all acids there, which would cause a really big jump in pH. So as I mentioned before, it really is the moles of your weak acid and conjugate base, or your weak base and conjugate acid in your buffer that's there to react. And that's why it's important when you make a buffer that you make it to the correct sort of molarity, and also think about what type of acid and base you may be adding to it to make sure that it could actually handle it. Otherwise, you will see a really big jump through it. Any questions on that there? Yeah. Either one. Yeah. 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 So here's the deal. We should keep it very simple this way, right? If you subtract a bigger number from a smaller number, you end up with what type of number? Negative. Can you have a negative moles or concentration? You cannot. It's a really good thing to keep in mind as you go through these problems, because I've seen it happen in people's problems. You should never end up with a negative concentration. So you want to think about like limiting reagent, so or excess reagent. So really, whichever one is the smaller number should always be the one you're subtracting, because otherwise you'll get a negative number. And this is going to be that one, because in most cases these are a one-to-one relationship, which means stoichiometry wise, whichever one's smaller is going to be really the limiting reagent in this case. Really, in this case, it is. So, and it's really because in this case here on this one, we did have plenty of the base part of the buffer, and that's really what's going to react with it. So really that was sort of in excess, and the other guy would be a limiting one. Yeah. Did I get your question, or yeah? Yeah. If you just have acetate in water. If you have acetate in water, it will accept the H plus from the water and produce OH minus and will become basic. Yeah. You could so I guess you could add more acetate in a situation like that, right? And what it's going to do is kind of like what we were talking about earlier. If we looked at just say this right here, right? You basically, this is kind of what you're describing in this situation. You basically have both of those guys in the solution, right? So, the only way it would really kind of shift equilibrium if you decide you want to add more acetate, right? It's going to actually shift it to the left at that point. And it would cause less H plus there. And, you would see sort of the pH, I won't say go basic, but it would be higher than say 4.74, which is maybe around what the pH of acetic acid would kind of be in that solution. So you'll see it shift up a little bit if you decide to add some acetate to that. So if you leave that there, depending on 1 molar, they will come to equilibrium. And remember that basically because of it's sort of a common ion problem, what happens is, and the reason why we can use the Henderson-Hasselbalch equation is the change part, because that common ion is there, is very small as they're coming to equilibrium. So because that change part is really small, almost what you start with in terms of initial concentrations will be your final concentrations. And that's why we could go right into this equation here instead of doing like an ice table, because basically what we start with and what we end with, if we went through the bottom one and solve for X, it would be a really small number. I think we did on an earlier example where we did like the ice table, then we did it with the Henderson-Hasselbalch equation. So if you go back to that original example we did earlier in this chapter, when you solve for X, it was a really small number that when you put it into the equilibrium value, the equilibrium value and the initial value were pretty much the same number. And that's why it wouldn't cause that big of a, they're able to kind of maintain their initial concentrations when you put it in there. Yeah. Yeah. Other questions? Okay. All right. Why don't we try this one here? Let us do calculate the pH of a buffer made of 0.3 molar ammonia and 0.36 molar ammonium chloride. And what is the pH after we add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer? So in this case, we're not keeping the concentrations, I'm sorry, we're not keeping the volumes constant. So you do have to take them into account. And let me give you a Ka value, which probably would be helpful, I imagine. Let me see here. Let me just make up a Ka value now. Let's go with that looks about right. Let's go with the Ka value for NH4 plus. We'll go with 5.6 times 10 to the minus 10. So we're looking for two answers here. What is the pH of the initial buffer before you add anything to it? And then what is the pH after you add? Okay, let's take a look here. So let's take a look at the first part, which is a buffer. So because it is a buffer, we could go right into the Henderson-Hasselbalch equation. And again, if we didn't know it was a buffer, wasn't told it was a buffer, again, we should be able to recognize this. NH3 is actually a weak base. And the NH4 plus here is going to be its conjugate acid in this case. So that definitely is the makings of a buffer. So for the first part here, we could just go into the Henderson-Hasselbalch equation. We could use the molarity. So we do want to calculate the pKa value here, which would be minus the log of 5.6 times 10 to the minus 10. In this case, I think it's a 925. So that gives us 9.25 plus the log. The base here is actually the NH3, which is the weak base. And if you weren't sure of that, that is a Ka, which means that's an acid, right? So that would be the acid part. So that's going to be 0.3 divided by 0.36 there. And that will get us 0.3 divided by 0.36 log. A opening pH here for our buffer of 9.17. Any questions on that first part? Once again, here you could do an ice table. You could actually do it two ways if you choose. You could do the ice table as the NH4 plus as an acid using the Ka value. You could also have done an ice table with NH3 using the Kb value and then convert it into pH as well. So you could have done either one, and they both should get you to the same spot. This is also a basic buffer, as we see, so the Henderson-Hasselbalch equation still works perfectly fine for it as well. Second part here, we're adding some sodium hydroxide here, so we are going to get a reaction between sodium hydroxide, and it should react with which part here of the buffer? Should react with the acid part, right? So we'll leave the Cl in there. You can take it out if you want, but basically we're going to get a couple of things made here. We are going to make NH3. We'll also make some water. And we'll make a little sodium chloride if you want to kind of keep track of everybody there. This table here, I should do molarity or moles? This table here, I should do moles because we are adding the sodium hydroxide, so we're adding volume. So we want to get the moles of our sodium hydroxide. So that is 20 liters, 20 milliliters, 0.02 liters times 0.05 gives us 0.001 moles here. And that is 0.2 liters times the molarity of 0.05 moles per liter. Yeah. We'll do the same thing for our ammonium chloride. Now, mind you, at this point, we have a buffer, right? That is 80 milliliters. And both of those guys are in there, the NH3 and the NH4 plus. So the volume is the same for both of them. So for our NH4Cl, 0.08, which is converting it into liters, times our NH4 plus, which is 0.36, gives us 0.0288 moles. For our NH3, we're going to do the same thing, 0.08, because there's 80 milliliters of the buffer, times 0.3, 0.0240 moles. Any questions on how I got any of those numbers there? Water, I'm not going to worry about. And sodium chloride, which is neutral, I'm not going to worry about either. So it keeps it a little bit simpler here. Change here going to be our smaller number. Our sodium hydroxide is the limiting reagent, should be used up. So that's going to be 0.001 minus 0.001 and a plus 0.001. That means at equilibrium here, we got none of that guy. We got 0.0288 plus 0.001 gets us 0.0298 moles. And 0.0240 minus, or actually plus 0.001 gets us 0.0250 moles. Any questions on that there? Yeah. For the first one? 0.0288. Felt like I hit the wrong number button there. 0.00. Just about to re-hit it. Thank you. 0.278. Thank you. What am I going to say? I'm just making sure you're paying attention. Yeah, I didn't screw up too much. All right, so 0.0278. Thank you. At this point, we do want to convert it back into molarity. So we want the total volume here. So total volume at this point is we started with 80 milliliters of the buffer. To that, we added 20 milliliters of our sodium hydroxide, which gives us a total volume at this point of 100 milliliters, which means we're really going to divide each of these guys by 0.1 liters, which is 100 milliliters, obviously converted. And that basically moves everybody over there to 0.278 molar and 0.250 molar at this point. At this point, once again, if you're not sure what you got going on, you still have a buffer, and you can verify that by looking at your ice table. Pretty much what we got left over is this guy and this guy, which again are still related to each other, and they are still a buffer. So there's still a buffer at this point. That means at this point, to get the pH, you can again ice table it if you like, or go back into the Henderson-Hasselbalch equation, which is what I'm going to do. I'm going to take the same pKa value plus the log of the base. Once again, this is the base. So 0.25 over 0.278. Gives me a pH of 9.20 at this point. Any questions on that there? Does it make sense? It does make sense. Our original buffer was 9.17. We added a little bit of base. It went to 9.20, which is the correct direction upwards since we added base, and it didn't go very far up. So that's pretty good too. So it means our buffer is pretty good in this case. Any questions on any part of that? Question on buffers, how to calculate it? Yes. Yeah, so any situation where you're basically adding volume to volume, which for our purposes in this chapter is like a buffer that you have, and you added either acid or base to your buffer, or as we're going to talk about next, titrations, where all you're doing is constantly adding volume. You should do the first ice table always in moles, and then convert it back to molarity afterwards. Other questions? Yes. Because pretty much this is a buffer, so it means that the buffer has an acid part, right, and a base part. And in this case, the acid part was the NH4Cl, and the base part is the NH3. And because I'm adding sodium hydroxide, which is a base, it should react with the acid, right? That's why they're called, right, acid-base reactions. So that's a good way to remember it, acid-base reactions. Those are two things that should react. You don't really hear too much about acid-acid reactions or base-base reactions. So that's a way to kind of remember that. Yeah. Other questions on buffers? So obviously you need to understand how a buffer works to maintain the pH. You need to be able to write these equations as you add acid or base to the buffer. And you need to be able to obviously calculate the pH of a buffer before you do anything to it. And then after you add acid or base to it. Any questions on how to do any of that calculations there? Okay, so that's one big topic down. We're off to the second big topic of the season here, and that is titrations. So the next thing we're going to talk about is titrations. And when we do a titration, we typically add a solution of known concentration to a solution of unknown concentration. And we use it in stoichiometry basically to calculate things like concentrations, equivalent mass, weight. So in a titration, basically we add known concentration is added to another of unknown concentration. And we typically use a burette, which is this guy here. Take the burette, and we could either have the acid or the base up here. And obviously we would have the opposite down here, the acid in this example. And we add like the base to the acid here. We continue to add base to acid or acid to base, depending on the type of titration you're doing, until we reach what is known as the equivalence point. And an equivalence point in an acid-base titration, that is the point where exactly the moles of the acid will equal the moles of the base. So technically the equivalence point is that exact point where pretty much you've neutralized everybody. You've added the exact amount of base that you need to neutralize the acid, or vice versa. That is not to be confused with the end point of a titration, which is pretty much where you stop your titration. If you do a good titration, those two guys should be pretty much the same spot, hopefully, or pretty close to each other when you do it. How do you know when you should stop your titration? Typically, we use an indicator, and an indicator is a substance that will change color near the equivalence point. Indicators pretty much work over a pH range. So they work over a specific pH range where they have some different colors depending on what the pH of the solution is at that point. So typically you want to pick an indicator, as we'll talk about, that will actually change color near your equivalence point. Most of the time, if you've done titrations before, right, they still do that in 50. It looked like they were doing that today over there. Right, you maybe have used phenolphthalein, yes, as the indicator, and phenolphthalein is an indicator that's used a lot with acid-base titrations. It works over a pH range of 8.3 to like 10. And this side of the range is pink. The other side is actually colorless there. So something like phenolphthalein is actually colorless in acidic solution. It's actually colorless in neutral solution, but it does turn a pink color in a basic solution. Nobody had anybody in their class put the phenolphthalein in their tub of sodium hydroxide. Always somebody that does that in that experiment. But if you did, it would turn very pink. Yes, and your titration would be over right at the beginning because all your sodium hydroxide is pink. So we go until you get the lightest shade of pink, right? When you use something like phenolphthalein, is what they always yell at you. And we will talk about why they yell at you about that as well. We'll also answer the age-old question of what you hear when people do titrations, and perhaps you heard it when you did titrations, or maybe you even said it yourself. I don't get it. I just added 1 drop and it went like super pink. It was like no color. I added 1 drop. Then your Chem 50 teacher said, do it again. I hope not. They didn't tell you to do it again. I hope they did. They were lying to you, right? Didn't you do it again? But some mean ones are like, oh, it's too dark. Get it lighter. Then you have people coming up to you. Is this light enough? I say the magic words like extra and credit, and then all of a sudden everybody can get light pink. It's amazing. They all shove it in front of my face. Does this look light enough? So we'll answer that question as to why you actually do see that. And it happens to like everybody, right? You have that one drop, you have like the color goes away and there's no color, and then you have the drop and it's like super pink. So we'll answer that question as to why that happens as we go through these titrations as well. So we're going to talk about several different types of titrations. So the first type of titration we're going to actually talk about is a titration of a strong acid and a strong base. So just for orientation purposes here, we'll look at, super zoomed in there. No. We'll look at a titration, say, of HCl and sodium hydroxide, which obviously is a strong acid, right? And a strong base. Going to give us a little bit of, you know, something water, I think, and a little sodium chloride action happening. So just so we're clear, in this titration here, up in the burette is our sodium hydroxide. So we're adding the sodium hydroxide to our HCl, which is down in the beaker here. And we probably got some indicator maybe in there as well. So what we're looking at here is a titration curve, and this is a typical titration curve. It's typically a lot of times this sort of S shape that we see here, and you kind of come in through here and coming up and coming across in this S shape. So there's really, when we look at a titration curve, pretty much kind of 4 distinct parts of the titration curve are the actual titration here. The first part is basically before we add any sodium hydroxide in this example. Then the second part is really from when we start adding to before the equivalence point. So kind of before the equivalence point. The third part that's important in this titration curve is the equivalence point. So that third part there, which is the equivalence point. And then the fourth part is kind of after the equivalence point. So in most of your titration experiences, you probably didn't go past the equivalence point. That's usually where you laid it up. When we start titrating in a couple of weeks or so, you will continue on past the equivalence point to get the full curve. It will get you that top part of the curve. So that's something, you know, you probably haven't done before, kind of past it, the equivalence point. So in all titration curves, there's pretty much these 4 most important spots. And there's different sort of ways that you have to kind of do the calculations depending on what type of titration you're doing and pretty much where you are in the titration curve. It's really important to understand where you are in the titration curve, because as we'll go through this, it pretty much could let you know the type of problem you should be doing before you even do the calculation. So if you understand sort of where you are in the titration, it's really important in understanding, you know, kind of what you should do. So let's take a look at this. We're just going to use some basic numbers where I'm just going to make up some easy numbers like 2s and 4s and 6s. So for future reference, that's where those numbers are coming from. I'm just making them up. So we'll start with really the first part here, which is before we add any base. So before we add any base, or in this case specifically sodium hydroxide in this example, the only thing that we have floating around in this beaker would be our HCl, right? Which basically is H plus and Cl minus, right? So if I wanted to figure out the pH at this point, how would I figure out the pH at this point? So if I know the concentration of the strong acid I started with, how can I figure out the pH? How do you figure out the pH of a strong acid? Yeah, so because it's a strong acid here, like HCl, when it goes for a swim, it's going to 100%, right, break apart into H plus and Cl minus, which means you will know the H plus concentration, which means you could directly at this point go right into, as you said there, the pH equation minus the log of the H plus, And that will give you your opening pH here. You could use the molarity here because we have not added anything, right? So we haven't added volume. So you could just use the actual molarity of the strong acid, which in a lot of cases, because a lot of strong acids are kind of like a monoproduct situation, the concentration of the strong acid is the concentration of the H plus, and you go right into the pH, and you'll have your pH. Should be acidic, as we see here on our graph there at number 1. We're under a pH of 2, so that definitely is acidic. Now we're going to actually start adding some base, and as we see, as we add base, our pH is starting to climb a little bit as we go through it. So let's talk about what happens at the point where we actually just start adding some sodium hydroxide from the very first drop to all the way to right before the equivalence point. Let's talk about how you go about sort of figuring out the pH at that point. Well, at step number 2 there, we are adding some sodium hydroxide to the HCl. That means we are going to get a reaction. So we're going to get a reaction of our sodium hydroxide plus our HCl is going to give us, once again here, some water and some sodium chloride. So initially here, this is what we started with. This is what we're adding, right? So let's just say, for example, first off, when I do this ice table, should this ice table be done in molarity or moles? Should be done in moles, right? Because we're adding, right? So we're adding sodium hydroxide to it. So that is definitely volume changing pretty much the entire way through your titration. All you're doing is adding volume. So constantly the molarity is changing, but the mole stays the same. So you should always do moles here on definitely the first table of a titration. So I'm going to, once again here, make up a number. And we're going to start with 4 moles of HCl. So that's in our beaker, right? So remember, it's in our beaker there. We have our sodium hydroxide. We're about ready to add to it. I got 4 moles of this guy in there. If I am really before the equivalence point here, which is where we're talking about, should the moles of sodium hydroxide be less than, equal to, or greater than the acid I started with if I'm before the equivalence point? It should be, I think I heard it, less. And that is because at the equivalence point, the moles of acid is what? Equal to the moles of base. So at the equivalence point, those two things are equal to each other, which means before the equivalence point, what we're adding hasn't got there yet, right? Because we're adding it, so it hasn't got to be unequal yet. So whatever we're adding needs to be less than what we started with. So again here, just making up a number, I'm going to go with 2 moles for this guy. And we would have obviously 0 this guy. That means when I get to my change part, what should happen to the sodium hydroxide here? It is going to be the limiting reagent, right? It is actually going to get used up because we got plenty of HCl to do that with. So the change part here will be minus 2 moles, plus 2 moles. That means when we reach equilibrium, I got nothing of that guy. I have 2 moles of this guy, and I have 2 moles of this guy. So that is sort of what the ice table should look like during a titration here. And as we talked about, as soon as you do the first ice table here, you should then convert these guys back to molarity. So we would use our total volume. So how much acid you started with, how much you added, to convert it back to molarity for each of these guys. Now, at this point, you could also use your ice table here to understand what is going on if you're not sure. So I have some sodium chloride and I have some HCl left over at this point. Is that a buffer? It is not a buffer because HCl is a strong acid. So once again, you cannot have a buffer that's made up of a strong acid. So although they may be related to each other, it's definitely not a buffer. So sodium chloride, as we've talked about before, is what type of salt? It is neutral, which means, frankly, I'm not all that concerned with it, right? That means really the only thing that we have left at this point is still our strong acid, which means basically we have the concentration of our H plus, which means you could then go into the pH equation, right? Minus the log of the H plus. And you can get your pH. So in this type of titration, once you start actually doing the titration, you need to do one ice table. The purpose of the ice table, which should be done in moles, is to figure out how much of your strong acid you got left over, because you're going to use up some of your strong acid, but not all of it. So you need to figure out basically from that ice table, what is the concentration of the strong acid left over at that point, because it's a strong acid, right into the Henderson-Hausbach here, right into the pH equation, and you will be able to get your pH at that point. Any questions on that part? So let us talk then about what happens as we get to the equivalence point. And let us first answer the mystery of why when I add one drop, it goes crazily pink. As I approach the equivalence point here, you typically see kind of a jump in pH to the equivalence point, and then you kind of see a jump in pH after the equivalence point. And if we look at this as we approach the equivalence point coming up, right there in that region, does the pH change a lot as you go to the equivalence point and then past the equivalence point? Does pH change a lot? It does change a lot, right? So as this is past the equivalence point, this is the equivalence point, and this is approaching the equivalence point. So the pH is constantly increasing, right? Now, because it's pretty vertical as I'm going through the equivalence point and then past the equivalence point, am I adding a lot of volume? I am not. It's vertical, which means not a lot of volume, like I only added one drop volume, yes? So even though you added only one drop, it could cause the pH to actually change by a lot, right? And because something like phenolphthalein works over a pH range, like 8.3 to 10, your one drop might have put you over here in like the 10-ish range or 9-ish range, which means it's going to be super pink as opposed to colorless over here on this part. Now, because you only technically added one drop to make that big giant jump in color, is the volume of your one drop, even though you may be over here, right? Very different from the volume that you see at the equivalence point. It is not. So even though you went super dark with one drop, it wouldn't have made a difference in your calculation because the volume would have been basically the same. So you didn't need to redo it. The reason they maybe told you to redo it is what happens if I really wasn't being very careful and I titrated like I did. Like I just open it up and walk away for a while, come back and shut it off. My dark pink color could actually put me over here, right? Which would be way far away from the equivalence point. So if you actually were doing your titration, you're really, really careful, and it really was just like one drop that made it go really that dark pink, you would have been okay in your calculation because you actually would have had pretty much the right volume at that point. But if you really weren't being careful and you just kind of open it up, shut it, open up, shut it, you could actually find it way far away in terms of the volume, and it would have made a difference and stuff like that. Any questions as to why it changes colors? I'll pass. All right. A bad, good. All right. Now let's talk about what happens when we do get to the equivalence point in this case. When we get to that equivalence point, we have exactly the same reaction sort of happening. So we got a little HCl plus some sodium hydroxide. Gives you some H2O and some sodium chloride. So once again, I'm going to, we're starting with our HCl in the beaker. We're adding this guy. So once again, I'm going to make up my number here as 4 moles of HCl. which means if I am at the equivalence point, how many moles of sodium hydroxide should I have? Should have 4 moles, should be the same, yeah, because we're at the equivalence point, and 0. That means you can't really screw the change up here. It is 4 in this case. It is the same number, which means 0, 0, and 4 moles, which you can then convert back to molarity using the total volume. At this point, the only thing that I have left is this guy, right? Our sodium chloride. And once again, that is a neutral salt, which means in this titration at the equivalence point, the pH should be 7. Yeah, should be neutral because it is a neutral salt. We have no acid or base left at this point. We have just a neutral salt that will not go through hydrolysis. So we should actually get a pH of 7. Which is pretty much what we see there. pH is 7 right there at the equivalence point, which is good. Now, sometimes they're not nice and tell you the volume to reach the equivalence point. If I need to figure out the way to figure out the volume to reach the equivalence point, how could I do that? If I'm not told the volume to reach the equivalence point. If it is a 1-to-1 relationship between the acid and the base, the mole-to-mole relationship, you could do a little M1V1 equals M2V2 action. If it is not a 1-to-1 relationship, you cannot do that because you'll have the wrong mole-to-mole relationship and you need to take it into account. The other thing that you could do is, you know for sure, like we just talked about there, how many moles of this you should have, and you most likely will have the molarity. So because molarity is moles per liter, I know how many moles I should have. I know the molarity. I can figure out the volume to reach the equivalence point. So there's a couple of quick ways to figure out the volume to reach the equivalence point, and you sometimes need to do that. So sometimes the list straight up asks, what is the pH at the equivalence point, and not really give you, you know, you added this much or something like that. So those are things you need to be able to figure out. Any questions on that? Okay, so to finish up this titration curve here, we decide, hey, it turned pink. That is not going to stop me. We're going to keep going past the equivalence point. So let's talk about what happens when we do go past the equivalence point here. Past the equivalence point. The pink color is just a recommendation to stop. So once again, we have our equation or our reaction that's going to occur here. This type of titration. And again, this is what we're starting with in the beaker. This is what we're adding from the burette. If I take my 4 moles of HCl to start with, and I am past the equivalence point, how many moles of sodium hydroxide should I have? Should it be less than, equal to, or more? It should be more at this point, because at the equivalence point, they're equal, and you're adding sodium hydroxide, which means you're going to be more past the equivalence point. So I'll make up a number of 6 moles here. And 0. What happens now with the change part? What is actually going to be the change here? It is going to be the limiting one here, which is actually the acid in this case. So it'll be -4, -4, +4. That means when we're done, nothing there. We got 2 moles there, 4 moles there. We could again convert it into molarity, each of these. So what I'm left with is sodium hydroxide and sodium chloride. Is that a buffer? Are they related to each other? They are not related to each other. So once again, we have a salt that is neutral, so not important. What we have actually left over at this point is a strong base. And that's because you're frankly just dumping sodium hydroxide at this point into a beaker, basically. You're just adding sodium hydroxide or hydroxide. Because this is a strong base, that would give you your hydroxide concentration, which would allow you to calculate the pOH and then to the pH. So you got to do the pOH first and then get yourself to the pH. So in this type of titration, when you go past the equivalence point, you do need to do a ice table again in moles. The purpose of this ice table is really to figure out how much actually of your strong base you just dumped in there that's left over after it reacts. And once you have that, because it's a strong base, that will give you your hydroxide and thus your POH and then to your pH. Any questions on that there? So 4 different parts of this titration curve. In this particular titration, before you begin, it's a strong acid right into the pH equation. Before the equivalence point, from the first drop to before the equivalence point, requires 1 ice table in moles to figure out your concentration of your strong acid after it reacts. At the equivalence point in this type of titration, really nothing needed other than a right pH 7, because you should always end up with a neutral salt at this point. And at the 4th point here, which is past the equivalence point, does require 1 ice table done in moles. Purpose of that ice table is you're basically adding excess amount of hydroxide to figure out the concentration of hydroxide that you have left over, and that gets you to the POH and then to the pH. Any questions on that there? All right, we were laid up there, 1 titration curve down.